Hello students, welcome back to the Easy BTech YouTube channel and you are listening to the course of Signals and Systems. In the previous video what we have seen is the introduction to the topic, and then we finally concluded with the signal definition, and we have seen that we'll be dealing only with single valued signal and a one dimension signal. So in this video lecture I will be discussing about what is called classification of signals. So this topic is a bit elaborate, and hence I have split this topic into multiple videos which will be released soon. Yes, so in this video lecture, I will be talking about first classification, which is continuous time and discrete time signals, and then I talk about even and odd part of a signal, and I conclude this video lecture with even and odd parts of a signal. Okay, so first we will talk about what is called the continuous time and discrete time signals. Okay, so continuous time signal is usually represented as x of t. Here t is called independent variable, and x is called the dependent variable. X or x of t, we call it as a dependent variable. Okay, so similarly for discrete time case, it is represented, discrete time signal is represented as x of n, and here n is the independent variable and x of n would be the dependent variable. X of n is the dependent variable. So note that here the time t is always continuous, which means that it takes all the real values, and the amplitude of the signal, which is x of t, we call it as a dependent variable. It can take even complex values, so there is no constraint on the amplitude, but time is always real. Okay, so for example, I can have a signal like x of t equal to, let us say, cos t, so that's okay. So we call this kind of signal as a real signal. Why? Because it will take always the real value. So this kind of signals are possible. Similarly, I can have a signal of this form, x of t equal to e power jt. Note that e power jt is a complex function. Okay, so this is a complex signal. So this, what do you mean by a complex signal? The amplitude of the signal is complex, and hence we call that signal as a complex signal. So the signal can take complex value. Signal, in the sense, keep in mind that is always an amplitude, not time. So once I say a signal, it is always the amplitude. Okay, so amplitude of the signal can be complex, but time, which is independent variable, is always a real number. So time t, it always varies from minus infinity to plus infinity. Okay, so I'll write like this: the time t is continuous because it is real. Okay, so time t is continuous and varies from minus infinity to infinity. So, and it varies from minus infinity to plus infinity. Okay, same is the case here. So for discrete time signal, the independent variable n can take only integer values, and amplitude can be complex. Okay, so compare and contrast here. So in continuous time case, t is always a real number, but for discrete time case, n is an integer value. N is always an integer value. Amplitude in both the cases can be complex. In that way, we differentiate between continuous time and discrete time signal. So graphically we can represent a continuous time signal like this. Note that here I have taken example of a real signal in both the cases. Okay, so if you look at the amplitude of signal, that varies continuously with respect to time for continuous time case, and in discrete time case, amplitude of the signal will take only the amplitude of signal is defined only at discrete instance of time. Okay, so amplitude of signal is not continuous, it is discrete. So in that way we can differentiate between continuous time and discrete time signals. Okay, so next let's move on to the second classification, which is even and odd signals. First we will talk about what is an even signal, and then we move on to odd signal. Okay, so for continuous time case, any signal x of t is said to be even if it satisfies this condition. So what is that? X of minus t should be equal to x of t, and same rule applies for discrete time case, that is x of minus n should be x of n for the discrete time signal x of n to be even. Okay, right. And typical examples for continuous time case are x of t equal to cos t or t square or modulus of t. There are infinitely many possibilities. Okay, and for discrete time case also we have x of n equal to the examples given here, which are cos pi n by 4 e power minus n square and so on. So just to understand a bit in detail, let us take any example. Let us take for continuous time case x of t equal to, let us say, mod t. We will check whether this signal is even or not. So for that, what is that we have to do? We have to calculate x of minus t and compare that with x of t. X of t is already here, but what happens to x of minus t? So that turns out to be modulus of minus t. Okay, so but we know that if you apply modulus, what happens? The whole value will become positive, and hence what happens? This is nothing but modulus of t. But we know that modulus of t is nothing but x of t, and hence what is it we have seen? We have seen that x of minus t equal to x of t, which satisfies the definition of the signal to be even, and hence the given signal x of t equal to mod t is an even signal. In a similar way, we will take example for discrete time case x of n is equal to, let us take e power minus n square. We usually call this as a Gaussian function. Okay, yeah, so x of minus n, because to check the signal to be even or not, we have to check this condition. So to check this condition, we need two signals. What are they? X of n, and we need x of minus n. X of n is already there, so now we have to calculate x of minus n. So that turns out to be e power minus of, wherever there is n, we have to replace with minus n and whole square. So that turns out to be how much? E power minus n square. Why minus n whole square is nothing but minus n square, but e power minus n square is how much? That is nothing but our original signal x of n, and hence what is it we have proved? We have proved that x of minus n equal to x of n for the signal e power minus n square, and hence the given signal is an even signal. So in that way, we can have infinite number of examples, and this is the way how we have to check a given signal is even or not. Okay, so in a graphical representation we can see like this. So what is that we have to observe is, for an even signal, whatever the amplitude you have from 0 to infinity, you should have a same amplitude from 0 to minus infinity. So when whatever signal you have from t equal to 0 to infinity, for this signal we have 0 to half, it is 1, and same we should have from 0 to minus infinity, and hence from 0 to minus half, this amplitude is 1. So whatever you have for positive time values, same amplitude should be there for negative time values. Then we say that that particular signal is an even signal. So even for discrete time case, the same rule applies, except at origin. Okay, so because at origin we should have the fixed value. Okay, so if you look at the amplitude, x of 1 is some value, same is the value for x of minus 1, and this repeats for all the samples, and hence we say that this signal is an even signal. So similarly, as I said, we can have infinite number of examples. This is just a graphical representation of an even signal. Next, let's talk about an odd signal. So how do you represent, how do you check whether a signal is odd or not? Okay, for a continuous time case, we have to see whether this condition is satisfied or not. So what is that? X of minus t should be negative of x of t. If this condition is satisfied, then we say that the given signal x of t is odd. Okay, and same rule applies for discrete time case. So what do I mean by that? X of minus n should be equal to negative of x of n. Then we say that the given signal x of n, discrete time signal x of n, is an odd signal. Okay, and again typical examples for continuous time case are x of t equal to sine t, t cube, t power 5, t power 7, and so on. And for discrete time case, x of n Few examples would be sine pi n by 6, n into e power minus n square, just n, n cube, n power 7, and so on. All those are examples of an even signal. Again, just to understand this a bit further, let us take one example. So we'll take x of t is equal to t. So definitely we will check whether this signal is an odd signal or not. So to check a given signal is odd or not, we have to check this condition. So to check this condition, we need x of t. It's already there, but we need x of minus t also. So what will be our x of minus t? Wherever there is t, replace with minus t. So we get minus t. We have t here, that t should be replaced with minus t. Okay. So but we know that t is nothing but our x of t, and hence this is equal to minus x of t. But okay, what is that we have got? We have got that x of minus t equal to minus x of t, and which is nothing but this condition, and hence we say that the signal x of t equal to t is an odd signal. We'll take one more example for discrete time case. Let us take x of n equal to sine of pi n by 6. So we need to check whether this signal is odd or not. Again, what is the rule? We have to check this condition. To check that condition, we need x of minus n. So that is nothing but sine of minus pi n by 6. But we know that sine of minus theta equal to minus sine theta. So you get minus sine of pi n by 6, and that would be equal to how much? So sine pi n by 6 is nothing but our x of n, and hence you get x of minus n to be equal to minus x of n, and hence because this condition is satisfied, we say that the signal x of n equal to sine pi n by 6 is an odd signal. Okay, and in graphical representation, any odd signal can be represented in this form. Okay, again I repeat, here I assume the amplitude of the signal is real. Okay, so to understand the concept of graphical representation of an odd signal, I took a real signal. So the signal can be complex also, and still it can be an odd function also. We will see that when we solve problems. Okay, so look at this signal. So why is this an odd signal? What does it say? So whatever amplitude you have from 0 to infinity, you should have a negative of that amplitude for negative values of time. Okay, from 0 to infinity we have this shape, and 0 to minus infinity we should have a negative of that shape, which is here. And if this condition is satisfied, then we say that signal is an odd signal. Okay, same is the case here. If you look at this discrete time signal, so whatever you have from 0 to infinity, we will leave 0 for discrete time case. So whatever you have from 1 to infinity, we should have the negative of that amplitude from 1 to minus infinity, if that is what happens here. So from 1 to infinity we have this shape, and -1 to minus infinity we have a negative of that shape, and hence what do we say? We say that that particular signal is an odd signal. Okay, so few properties which are satisfied by this even or odd signals is here. So first property says that for an odd signal, its value at origin is 0. What do I mean by that? So let us take a continuous time signal which is odd. It means that signal should satisfy which property? X of minus t equal to minus x of t. So what does it say? It is an odd signal, so definitely this condition should be satisfied, and it is asking the value at origin. So if you want value at origin, so what should we do? We should replace t with 0. So if you replace t with 0, you get x of 0 is equal to, because minus times 0 is 0, is equal to minus, again you have to replace t with 0. So you have got x of 0 equal to minus x of 0. So this implies 2 times x of 0 equal to 0, and this finally implies x of 0 equal to 0. Why? Because 2 cannot be equal to 0. X of 0 should be equal to 0. So that's what the claim says. It says that the value of the signal at origin equal to 0. So same rule applies for discrete time case also. You can just check that out. So how do I check? I'll just write the condition and then I will leave it as homework. Okay, so we need to check the value of the signal at n equal to 0. When n equal to 0, what happens? The same steps repeats, and finally you can prove that x of 0 equal to 0. You can readily see that from previous example, right? So the value of the signal to origin is 0. But what happens for this signal? What is the value of the signal at origin? We will discuss about that when we talk about Fourier series. Okay, you have to wait till that time. Why? What is the value of this signal at origin? So there is some discontinuity, and how do you evaluate the value at origin? So that we will see later. Okay, but definitely that value would be equal to how much? 0. Okay, right. Next, so what is the second property? If you add two even signals, the resulting signal is also even. It means the sum of two even signals is even. So for example, we have two even signals x1 of t, which means x1 of minus t is equal to x1 of t, and I have another signal x2 of t, which is also even, and hence x2 of minus t should be equal to x2 of t. Okay, now if you add them, what happens? X1 of t plus x2 of t, let me assume that is equal to x3 of t. Okay, so what happened? It will be x3 of t. So we should check whether x3 of t is an even or not. So what is that we have to do? We have to replace t with minus t. Sorry that I am writing in a reverse direction. But what happens if we replace t with minus t? So we get x1 of minus t. Why? Wherever there is t, we have to replace with minus t plus x2 of minus t. But what is that we have seen? We know that, okay, I'll write here. Yes. So, but we know that x1 of minus t is how much? X1 of t, and hence we can replace the first term with x1 of t plus x2 of minus t with x2 of t. Why? X2 of t is also odd. So this is equal to x3 of minus t. But what is x1 of t plus x2 of t? That is nothing but our x3 of t. So what is it you have got? You have got that x3 of minus t equal to x3 of t. That means what? The given signal x3 of t is even. Okay, one more property is sum of two odd signals is odd. See, note that whatever we have seen before is equally applicable for discrete time case. Okay, and hence I am not trying to prove that again. Okay, so you can just replace t with n and the parenthesis with square bracket, then everything remains same for discrete time case. Whenever there is difference, definitely we will see them separately. Okay, so next property, it says that sum of odd signals is odd. Okay, if you add two odd signals, the resulting signal is also odd. So I will prove this by taking discrete time signal. Okay, so we have two signals x1 of n, with two signals x1 of n and x2 of n, and they are assumed to be odd, and hence what happens? X1 of minus n is equal to minus x1 of n, and x2 of minus n is equal to minus x2 of n, because they are assumed to be odd. Now if you add them, okay, let me assume that addition of these two signals is x3 of n, that is I'm adding x1 of n and x2 of n. Okay, so x1 of n and x2 of n, I want to check whether addition of these two signals, which is x3 of n, it also is odd or not. So again, what is that we have to do to check whether the signal is odd or not? We have to replace n with minus n. So if you replace n with minus n, we get x1 of minus n, because we have n here, we have to replace that with minus n, plus x2 of n should be replaced with minus n. Okay, but we know that x1 of minus n is how much here? Minus x1 of n. Okay, and x2 of minus n is how much? That is minus x2 of n. So we can easily see that this is nothing but how much? Minus x3 of n. Why? If you take minus out, you will get x1 of n plus x2 of n, which is nothing but x3 of n. So what is that we have proved? We have proved that x3 of minus n equal to minus x3 of n. So that implies what? If you add two odd signals, the resulting signal is also odd. Okay, right. So the last property would be, again, as I said, even though I have proved this for discrete time case, again same rule is applicable for continuous time case also. Okay, right. So one more last property is that if you add an even and odd signal, then resulting signal is neither even nor odd. So for example, let us take x1 of t to be equal to cos t. We have seen that this is even, and I take second signal x2 of t which is equal to sin t, and we know that this is an odd signal. So if you add them, let me call that as x of t which is equal to x1 of t plus x2 of t. Okay, so this turns out to be how much? Cos t plus sin t. Now I want to check whether this new signal x of t is even or not. So what is that I have to do? I have to replace t with minus t. If you replace t with minus t, what you will get? Cos of, wherever there is t, you have to replace with minus t. So cos of minus t is cos t. Where again, wherever there is t, you have to replace with minus t. Sine of minus t is minus sin t. So definitely, what is this signal? Like this is not nowhere related to x of t. We cannot write this. This is not equal to x of t, and again this is not equal to minus x of t, and hence what does it mean? It means that that signal x of t is neither even nor odd. So if you add an even signal and an odd signal, the resulting signal is neither even nor odd. Okay, so next, one more important property comes from the product. So if you multiply two even signals, the resulting signal is also an even signal. Okay, so again I have taken two signals which are even, x1 of minus t equal to x1 of t and x2 of minus t equal to x2 of t. Because we assume that these signals are even, they should satisfy this property. Now I define third signal x3 of t, which is product of these two guys, x1 of t and x2 of t. So now I want to check whether this signal x3 of t is even or not. So what should I do? I should replace t with minus t. So what do you get? x3 of minus t is equal to x1 of minus t. Note that we have to replace t with minus t. So you get x1 of minus t multiplied with x2 of minus t. But we know that they are even signals, and hence this should be equal to x1 of t multiplied with x2 of t. So what is that we have got? We have got the final answer to be x1 of t multiplied with x2 of t, but that is nothing but our x3 of t. So what does that mean? We have proved that x3 of minus t equal to x3 of t. So that implies the product. What is x3 of t? x3 of t is nothing but product of signals x1 and x2. And hence what is that we have proved? We have proved that the product of two even signals is even. Again, same rule applies for discrete time case. So I'll give discrete time case proof as homework. Okay, so please try to prove that result. Okay, that's just for practice. Okay, right. So again, if you multiply an two odd signals, the resulting signal is odd. Okay, so because the signals are odd, so like we can write down x1 of minus t is equal to minus x1 of t. We have to take two odd signals, so we need x1 of minus t equal to minus x1 of t and x2 of minus t equal to minus x2 of t. Again, how do you proceed to check the proof? You have to take x3 of t and you have to take the product, right? So we should take the product of them, which is x1 of t multiplied with x2 of t. Now I have to check whether this product is odd. What happens to this product if you replace t with minus t? So let us do that. So if you replace t with minus t, x3 of minus t would be equal to x1 of minus t multiplied with x2 of minus t. But we know that x1 of minus t equal to how much? Minus x1 of t, and similarly x2 of minus t would be equal to how much? Minus x2 of t. Definitely, what is that we have got? So this turns out to be minus times minus is plus, and finally you get x1 of t multiplied with x2 of t. But what is x1 of t multiplied with x2 of t? That is nothing but our x3 of t, and hence what is that? we have proved that the product of two odd signals results in an even signal. Okay, so if you multiply two even signals, it's an even signal. If you multiply two odd signals, still it is an odd signal. But what happens if you multiply an even signal and an odd signal? The resulting signal is an odd signal. Okay, so proof again, I will give this as homework. Okay, so please try to prove this. Okay, so if you multiply an even signal and odd signal, okay, you should get an odd signal. So what is that you have to do? You have to choose two signals. First one is x1 of t, which is an even signal. Second one is an odd signal, x2 of t. So you take the product and check whether the product is an odd signal or not. I will leave that as homework. Right. So next, let's move on to the last topic, which is even and odd part of a signal. Last topic of this lecture. Okay. So even and odd parts of a signal. Okay. So what happens is that in general, a given signal is neither even or not. So some signals satisfy those properties, but all signals need not satisfy those properties. So for example, I take x of t. Okay, I'll take an example like x of t equal to e power t. That flow is neither even nor odd. So you can take any number of infinite number of examples which are neither even nor odd. Okay, so in general what happens is that the given signal is neither even nor odd, but what happens is that we can split that signal into even and odd parts. How do you do that? In continuous time case, we write the signal x of t to be equal to what? Xe of t, which stands for even part, plus xo of t, which stands for odd part. Okay, xe of t stands for even part, xo of t stands for odd part. So what is that we are doing? We are splitting the signal x of t into even part plus odd part. Okay, same rule applies for discrete time case. A discrete time signal x of n can be split in the sense you can add them. Okay, add them into x. You can split them into xe of n, which is even part, plus xo of n, which is an odd part. Okay, but how do you derive these functions, even part and odd part of a signal? Okay, so xe of t, I will derive it for continuous time case. Same rule applies for discrete time case. Okay, so it is given that name itself suggests that even part is even, means what? Xe of minus t should be equal to xe of t. Okay, so similarly, odd part name itself suggests that odd part is there, and hence that should be equal to minus xo of t. Okay, so odd part should be odd and even part should be even, because name itself suggests that it's an even part and odd part. Okay, so what is that we have to do now? Now I replace t with minus t in this equation. Okay, I'll replace t with minus t in this equation. So what will happen? X of minus t would be equal to how much here? Xe of minus t, because I replace t with minus t, plus xo of minus t. Okay, but we know that even part is even and odd part is odd, so I can replace this with xe of t minus xo of t. Okay, I can replace that with xe of t minus xo of t. Why? Odd part is odd. Now you look at these two equations. Okay, if I add them, what happens? If I add them, so the starred equations, if I add them, what happens there? Left hand side you get x of t plus x of minus t, and right hand side what happens? Xe of t plus xe of t would be 2xe of t, but what happens to xo of t? That gets cancelled, and to get even part, what is that you have to do? You send to that side. Okay, so finally how does that look? This implies x of t plus x of minus t would be equal to how much? 2xe of t. Correct, because you're adding these two equations, because xo of t will get cancelled out, and you can send to that side to get the even part. Similarly, if you subtract, okay, so second equation from first equation, what happens if you subtract second equation from first equation? Xe of t will get cancelled out, so xo of t minus xo of t would be how much? 2xo of t. So that I will write down x of t minus x of minus t would be equal to how much? 2xo of t. Again, you send 2 that side, you get to the odd part. Okay, so in that way, what is it? Same rule applies for discrete time case, even though I have proved only for continuous time case. So what happens? Finally, we get even part to be, we have derived this right in previous slide. So we got x of t plus x of minus t equal to 2xe of t, and hence you get xe of t to be equal to x of t plus x of minus t by 2, and similarly x of t minus x of minus t whole divided by 2 would be equal to x of t. Okay, in that way we derive the even and odd parts of a signal. So if a signal is neither even nor odd in general, which is the case for most of the signals, we can split the signal into even and odd parts in this fashion. Again, the same rule applies for discrete time case. Okay. Right, I think I will stop here and I'll continue with the examples in the next lecture. Thank you.